Okay. In a survey, U.S. adults were asked to identify what devices they use to access social media. The results are shown in the figure. Now, look at the figure to the left. This is the results of their survey. 94% use a computer, 46 use a cell phone, 16 a tablet, 7 blah 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 blah. How come those don't add up to 100? 204. They can use more than one. They asked them what devices they use. So apparently they could say yes to more than one. So first we're going to keep that in mind. And then we're going to see if this is binomial. You randomly select your 7 workers and you ask them if they use a cell phone to access social media. I either want them to say cell phone yes, cell phone no. So that part's good, right? The probability is going to change throughout my experiment? No, it's fixed. So binomial, yes or no? Cell yes. Anything else? No. We're good. So we're using this, we're picking 7 people at random to ask them, based on the results that we have. Our probability is, what was the probability for the cell phone in there? 46%. And how do I get my probability that it's not? Subtract it from 1. I can't add up all the others because they don't add up to 1. So I subtract this guy from 1. And my x will go from 0 to 7. Okay, now, we have a binomial, and we can run it 2 different ways, just like we talked about yesterday. You can use your sync, because it doesn't matter what order we get these in. Your successes are measured first, then your failures, that's the 7 minus this. Each time you do this, you're going to have to change this one, and this one. And you can run your whole table. Or you can do second pairs, binomial PDF, binomial, probability, distribution, function. For those of you that have the 83s, the old calcs, N, comma P, comma X. The new calcs will ask you number of trials, P, X. Just paste it. Paste it in and enter, second enter, and fill in from 0. So in other words, I would put the first one in as 7.460. Change this one to a 1, to a 2, to a 3, to a 4, 5. That's what we did, 0 to 7. No, it won't work, because you can't do all those at the same time. You can only do one at a time. Oh. And then just do second enter, change it to a 1, change it to a 2. Okay, so they kind of worked out all the probabilities. They did their sync. Are you comfortable with that? They use sync. I don't care which one you use, as long as you're comfortable with one of them. Now, generally 3 positions. They did go 4. That's okay. I'll change it to 3. And quick, what should they add up to? 1. That's your probability distribution. Your probabilities are between 0 and 1, and the sum of your probabilities are 1. Now, from this table, this is where you answer all your questions. What is the probability that out of the 7 people we asked at random, exactly 3 said yes? Up about 29%. The probability is about 29% that exactly 3 out of those 7 will say yes, they use a cell phone. What is the probability that at most 4? I would add up from here to 4. Now, could I ask somebody to kindly add those up for me, please? Ricky, can you give me my better upper? This is at most 4. Only until 4. That's the most it could go to. 4. Okay, now, I want to show you what the binomial CDF is. C stands for cumulative. You know when you do your cumulative histogram, you start at the 0 and you keep adding all the way each time? We do the same thing here. We start at the 0 and we keep adding up until we hit the number that we want to hit. It only works from the lowest to the highest. It doesn't work the other way around. Like I can't go from 5 to 7. I can only start at the 0. Accumulate from the 0 to this. So if you run your cumulative and you say this, 0.46 up to the 4, it will equal 0.834. It starts at the 0, smallest to the one you want to go to. Now, if I asked you what was the probability of at least 5, notice the 5 is from here down. Could I use my complement now? Well, yeah, couldn't I use my complement for this guy? Take 1 minus that and use my complement? So that 1, yeah. I think it's easier on your table to see when you can use your complement because nothing overlaps. I got to cover the whole board here. But I can't use my cumulative for this because my cumulative only starts from the 0 on up. If I wanted to, I could do this. 1 minus my binomial CDF. And do my 0 to 4 on this guy. Do it up to the 4. This is one of the reasons why I don't really use the CDF, because you really have to make sure you start from the 0 on up. In our tables, it's probably just easier to just add them up rather than try to figure out where did I have to go with them? You know, which way am I going? So the CDF is there, but we're going to use that PDF for each individual probability, and you can use the CDF if you so desire. Okay, what I want you guys to do is try it yourself 3. So we know this is binomial. The probability of success we said was 16. And a 7. Everybody was able to do this without a problem? Anybody struggling? No? This is nice. Be careful of your scientific notation numbers. Move the zeros. Now this one, could you round this to the 1 decimal, please? I left it go out because I wanted you to see the 4 zeros, but absolutely. And then this one, the 5 zeros. Don't leave it 2.7 because that's wrong. The chart on the top of the page there. See that chart that looks like they're reading off of the tablet? Oh, okay. So that's for each piece that they're doing. That's where the 16 came from. Yes, you can put 003. You're going to see 2.7 times e to the something. So I left it there so you recognize it. Because if I changed it to 3, I didn't want you not to recognize the e part. Oh. Same thing with the 99. This is what I just said. I left it here, so if it said 9.9 e, you wouldn't say, well, where'd the 9.9 go? You'd see 9.9, and then I rounded them. Now, y, this is a little different than the other one. The other ones, the probabilities were kind of almost symmetrical. These, they're higher over here, and very, very small over here. Why are they so small down here? Why are these so small? Because why? Very good, Rachel. It's a very small percent that are going to say yes, they use their tablet. So would I expect more of the 7 people that I surveyed to say yes? I would expect less of them to say yes.
There's only like 3 zeros in the is there supposed to be 4 for the 0 for the 10 one?
For which one? For the 10? 4 zeros, 9, 9. But if you round to this position, then this has to be a 10. I left the 9, 9 so you would see where it came from. And again, we can ask ourselves the same things. We can say at most 2, more than 2. You can take them right off your table. Now, we're going to look at this skewing when we graph this, but as the probabilities get smaller, you expect your numbers up here to be higher. Makes sense, just like Rachel explained it. If the probability is small, not a lot of people are going to say yes. If the probability is larger, yeah, a lot of people are going to say yes. Like the surgeries we saw. The surgeries was like 85%, 90% chance of success. We had more higher probabilities and the more they did, which would make sense. So at the same time, I want this to make sense to you. All right, so let's jump over to number 5, to example 5, on page 206. Okay. And again, we're going to do the same things, and we're going to answer the questions when they get to us. And we're going to use your table. A survey of U.S. adults found that 62% of women believe that there is a link between violent video games and teens exhibiting violent behavior. That's an important fact, 62%. This is what the survey told us. Based on that survey result, we randomly select 4 women from the United States, and we say to them, do you believe that there is a link between playing violent video games and teens exhibiting violent behavior? And they're going to either answer yes or no. There's your binomial choice. So probability that they say yes is based on our survey. Probability that they say no, failure, is 1 minus this. The N, we asked 4 random people. And here's our results. Now, we do it the same exact way, binomial PDF. So I'm going to fill in, you don't have to do this part, I'm going to just fill it in, your book did it. I think they did all the C's, they used the C. So if you're interested to see how the C looks all the way down, it's a little bit longer to use the C. But if you turn to page 206, it uses the C for all of the Bernoulli's formula for all of this. Now, from this, we should be able to answer these questions. So what is the probability that exactly 2 said yes? %, 0.333. So 33.3%. There's a 33.3% probability that of the 4 people that I asked, exactly 2 of them said they believed there's a link between watching the games and being violent and having violent behavior. And that would be a good, pretty good, strong probability there. What is the probability that at least 2 of them, which ones am I looking for when I say at least 2? 2, 3, and 4. 2 or more. Think money in your pocket. You have at least $2. You could have 2 or 3 or 4. You're going to add these up. And that one's a little bit stronger. 0.843. Good. About 84% of the people would, 84% of the time, we would get 2 or at least 2 to respond yes. Now, watch this next one. Fewer than 2 respond yes. So, 0 and 1. Do you see off your table? That's your complement case. So I could do it 2 ways. I could do the 1 minus my 843, and that might be a little harder to subtract in my head. Or maybe these are just 2 pieces. I can pretty much add this in my head. It might be a little bit easier to just add those. But do you see the complement case exists for that? Right, so off the table, you can kind of see the difference in your complement case. Are we good with this? Okay. Real, it's going to be the same exact thing. We're going to have the same graph as we had in your probability distribution. So we're going to jump over to example 7. We're just going to use the chart because my goal is to graph.
Oh.
So we're going to pull your information out. Here's a survey. About 60% of cancer survivors are ages 65 and older. Good. 0.60 is the P. The Q. 0.40, and you can just say 0.6 or 0.4. And then we're going to select 6 cancer survivors and just ask them, are you 65 years or older? So they can say yes or no. So we're going to do this 6 times. Take this short one. Okay. We do it the same way, binomial PDF, so I'm just going to write the probabilities out here. The book has them done as well. My goal for this one is to graph, not to calculate, because we know how to do these. Okay, so now, because this is, again, your probability distribution function, we graph it just like we did your probability graphs that we did a couple of days ago. We use your XY axis, we give it a title. We give it an X value and a P of X. This is just like your relative frequency graph. Again, we've done this before. No different. Run your y-axis like money. If you can, go by 0.5s. If not, go by 0.10s. Do it like money so that you don't mess up your decimal. And your bars. Okay. So at the 0, you got a really little tiny bar. At the 1, a little bit bigger. 1, 3, 2, 7. I'm sorry? No, yeah, you just estimate where you're going. 0.311. We're just sketching. 0.1, I don't have a graph paper here. And 0.047. And again, we look at the skew to this. Now, their probabilities, guys, is greater than half. So I should see more of my probabilities, the higher ones, come later. Mostly because it's close to the 0.5. Right around the middle of this is where you're going to see most of your probabilities lie. And because it is a little higher, I notice they're more down here. It's shifted just a little bit. It's not symmetric. It's a little bit of a skew here. It's skewed to the left.
For the point, 138 is supposed to be lower than 0.5.
Am I close enough? My goal is to worry about this, but thank you. So now, if my skew is to the left, it means I have more that say yes than say no, right? That's because my probability is greater than 0.5. If my skew is to the right, and I put this on your notes, and I notice my graph goes like this, higher, lower, then we said your probability must have been smaller, right? For less people to have this. Less than 0.5. If I have no skew and I'm fairly symmetric, then my probability was 0.5. Or thereabouts 0.5. You can say approximately, it could be 0.52, 0.54, 0.48. They're approximately a normal distribution. You would expect to see this one and this one the same, look close enough, and the higher ones to be about the middle. Okay, so it's based on where your skewness goes, and that's based on the probability, which we already determined if you have a higher probability, your higher numbers are in the upper part of your table. A smaller probability, your upper numbers are in the beginning of your table. Make sense? Okay. Totally makes sense to us, right? I could absolutely put this in my L1, put this in my L2, just like we did your probability distribution function. It was there. L1, L2, find your mean, find your variance, find your standard deviation, and then back out of it and find your variance. But there's a little quicker way to do this. And there's 3 little formulas to do this. To find the mean, we multiply n, which is how many you surveyed, times the probability of success. To find the variance, we multiply all 3 of those pieces, and then the standard deviation, of course, is the square root of your variance. Okay? Now, this works well only in a binomial situation. Only binomial, a discrete binomial situation. So, because sometimes they don't give us a table to use. So if they don't give us a table, we can't use an L1, L2. So take a look at example 8. Example 8 says, and I am on the bottom of page 209. In Pittsburgh, Pennsylvania, about 56% of the days in a year are cloudy. Find the mean, the variance, and the standard deviation for the number of cloudy days in June. It didn't give me a probability table, so I can't do an L1, L2. But I can use this little formula. I know this is my probability of being cloudy. This is my probability of not being cloudy, the 1 minus this. Cloudy is my success this time. Not cloudy, sunny, is my failure this time. But they're asking for the number of cloudy days in June. So what is my n? 30. 30 days in June. I have all the information I need for this. I have no table. I can't do an L1 and L2. So I use my formulas. And they kind of like, once you get this part, you just multiply by the next part.
So the Q would be 0.44 equals
Well, your n is 30, your p is 0.56, your q is 1 minus 0.56. So n, 30, times p, and we found your mean. And yeah, and so just find your mean, 16.8. Remember, your mean is 1 decimal place more than your numbers, and your numbers were whole numbers for numbers in June. Now, to get the next part, notice they just took that, they multiplied by q. You already have n times p. That's 16.8. Multiply it by q. You get your variance. Okay? You already have the first part. So about 7.4. Wait, let me just finish this. Now, your standard deviation is the square root of this. So just take the square root of 7.4. And so that number is about 2.7. So you're kind of just going along with this. You do the first one, you got the n times p, then you multiply it by q, you got your variance, then you take the square root of your variance. Right? Because you have no table to do L1, L2. Questions?
I missed the part on the part before this.
Well, I'm not going backwards. This is where we are. So, any questions on this?
No.
No? Okay, do you see why we have to use those formulas? No one gave us a table. I don't know what each day was in June. So we're kind of stuck right here. All right, you guys try it yourself 8. Same setup, a little bit of a different scenario. Yeah. Try it yourself, number 8. Same setup, different month, different town. We're in California. We're 44% of the days are raining. This is still our probability of success, raining. What's your failure? 1 minus. And how many days in the month of May? 31. Again, we have no chart, so we use your formula. N times P. 31 times 0.44. This is your mean. You see what we're doing? We have no choice. We have to use our formulas.
It says 44% of the days in a year are clear.
Oh, clear. Sorry. I took the rainy, like the other one. Sorry about that. Clear. Good. And then these are not clear. Okay, so 13.64. Now, bring them along. This is your variance. N times P times Q. You have your N times P. Multiply it by your Q. And then take the square root of that for your standard deviation.